So are we all ready? Everybody here okay? I hope so. So back-to-back panel discussions today, and the next one up is from lemons to light power, and it's all about squeezing every drop of energy from your energy harvesting source. In the early days of my career, which was Texas Instruments, my favorite demo was showing how the then groundbreaking MSP430 microcontroller could be run from a lemon. And always created a lot of attention. Thankfully, technology has come on somewhat since then, and ultra-low power microcontrollers are readily available. And new energy harvesting sources have gone on to replace the lemon. And of course, along with the advanced PMICs that extract maximum energy from those energy sources, we have a good system to start working with. Combine these technologies with advanced power analysis capability, and you have the ideal recipe for a self-powered ambient IoT node. So to discuss this further, I'm joined by 4 key players in that space. So we have, first up, Edin Golubovic, who's VP of R&D at EnOcean. And EnOcean, you will perhaps know, were pioneers in the energy harvesting IoT space. We have Jeff Crystal, COO of Voltaic Systems. And Voltaic provide durable solar panels and scalable core solar systems that power IoT devices. Then we have Tristan Cool, fantastic name, by the way. Industrial IoT Marketing Manager at Silicon Labs. And you'll know Silicon Labs, I guess, as a leader in low power wireless connectivity. And then we have Björn Rosqvist from Qoitech. He's the CPO and co-founder of Qoitech. And Qoitech provide the OT product suite, which really helps developers design energy efficient devices. So with that said, I'd like to start with you, Edin, because EnOcean, I think, has the history in the energy harvesting space. It's been a pioneer in battery-free wireless technology, so from kinetic switches through to self-powered wireless sensor nodes. Give us a sense of the challenges you faced to get from those early days of kind of simple wireless switches to the complex integrated products that are available now.
Thank you very much. So our first major task as a company was proving that energy harvesting goes beyond those demos, lab demos that you showed. And we really had a nice entry point with the switch because the device is simple in function and doesn't require any continuous operation, and gets all of the energy from the user action. So that helped us establish ourselves. But where the real step came is when the customers started demanding battery-free, maintenance-free, self-powered multi-sensor devices that needed to work reliably. So basically, there we had to solve 3 main challenges. The first one was low-power radio design. The second one was the energy harvesting from multiple sources. And the third one is basically having a reliable energy storage for devices that on end have to work for weeks without getting additional energy inputs. Next to these, our customers asked us to basically to move from products to portfolio. To do this at scale in millions of the devices, we needed to solve hardware miniaturization issues and also develop firmware that can squeeze every available microjoule out of the surrounding. So basically from proof of concept to the devices that hide energy harvesting from customers, and customers just see the operation the devices without actually knowing their energy harvesting.
Just tell us a little bit more about because you started off by mentioning the wireless transceiver, I think, and having to develop something new, I guess, and ultra low power. So maybe you can give us a little bit more background on what that journey looked like as well.
Yeah. So at the time when we started, there was no Bluetooth low energy, there was no LoRa, there was almost none of these. So we basically had to create our own protocol and make it work either on the proprietary chips that didn't exist at that time, or make our own chips. So we started with making our own chips and our own protocol. For the first decade, that was our reality.
So not a trivial task, I think, to get the first products out of the door. So now, because you've described a lengthy journey there, and I think from going from that simple application, that sort of proof of concept, through to much more complex products. In your work with customers now, what are the new application scenarios that they bring that still challenge you?
Yeah, so we were traditionally active in smart building environments, and we have proven that energy harvesting works well in those environments. Nowadays, we are entering domains such as logistics, aerospace, healthcare, and each of these domains has its own challenges. So take an example of a solar asset tracker for containers. It may be exposed to the sun for a few days and then may go into the complete darkness for weeks. So you need basically energy systems that are adaptable to those. It goes without saying that, for example, acts such as EU Cyber Resilience Act is also putting a lot of strain on the battery-free devices, because we need to now do security and compliance, and also make sure that the devices are reliable within the same energy budget.
So there's a changing landscape from a compliance point of view, but also what you describe, I think, is that you have to think very much about the application and then the energy source according to the application. So let's move on to Jeff from Voltaic, because I want to dig into the energy sources a little bit more. So if we use that kind of wireless sensor module as our use case, so in a system like that, there are essentially three subsystems: power, sensing, and the wireless SoC itself, the wireless transceiver. So given a reliable power source, the sensing and the wireless elements of that, can I say, are relatively simple or straightforward. I guess none of it's simple, but let's use that word. In the world of energy harvesting, though, where available power can fluctuate, a question for you, Jeff, is really, what are the key design challenges with integration of solar as the power source, especially in an unpredictable environment?
Yeah, so I think there's a couple challenges. Energy, when you're thinking about from the sun, is always going to be a probability. So, and we can predict that probability based on typically location and time of year. But then if you have it on a moving asset, it could be a cow or it could be a shipping container, which is most common. You now add in probability of orientation and you add in probability of location. So sort of understanding how much energy is available is going to be a little bit of a complex little puzzle that we can model out, but we can also use tools like Qoitech to figure out. I think number two for us is always durability. So how does this last 10 years outside? And then the third challenge is with the solar panel is the power output characteristics vary based on how much sunlight is hitting it. So you need to have the PMIC and the circuit designed so that it can adapt to those variations.
So one of the considerations is environmental, then, the ability to withstand the environment that the panel is placed in. Then there's also the power output optimization, I guess, the PMIC system that you're talking about. So can you give us a sense of what that power system looks like?
So typically there's some energy harvesting element. A solar panel is one. That goes into a PMIC often, something like EPs, which does energy harvesting. I've seen also people use something as simple as a diode going into a storage device though. And then on the back end, it goes into some sort of storage element, often a battery, but ideally some other elements like a lithium-ion capacitor, and then an MCU. And one thing I think is sort of interesting from my customers is it used to be, companies with lots of firmware engineers were able to get into low power. And now, I have a customer in New Zealand, which is a very small team, and they're using your Gecko line. And it's not a big team. It's not very, I would say, as sophisticated as some other customers. And they're able to access sort of the same low power sort of designs that these used to be sort of only affordable to the brain power of these big teams.
Yeah, so in some ways, the technology that's becoming available is making it more accessible for companies and customers to be able to create ultra-low power designs.
Which then drives down cost.
Increases lifetime. Right. And I guess operational uptime for the customer as well, is the very end customer is a critical consideration. So let's work our way through the system a little bit then now, because I talked about the MSP430 and the ultra-low power microcontroller that was at that time. And Tristan, let's talk about the Silicon Labs technology here. So since those early days, the power profile requirements of MCUs, SoCs, and associated hardware has reduced dramatically. Methods of any energy creation that were previously unavailable are now a reality, as we've been discussing. So to capitalize on that, how has the fabric of devices changed to enable these reduced power requirements, and what are the critical features engineers should consider when selecting a device for, again, let's say our wireless sensor node?
Yeah, very good. That's a big question. It's a good one. I would say a lot has changed because in the IoT semiconductor space, our campaigns were literally ideal for battery-powered devices. We were boasting how well we were at a battery-powered device, and then along comes the likes of this market. Our claim to fame is batteryless. So I would say the harvesters are getting so much more efficient. We're seeing PMICs out of this world. We're seeing even the storage getting better and better. So the semiconductors need to follow in that design. Otherwise, we're wasting, it's all in vain. We're wasting the energy. So if we work our way up, from a semiconductor standpoint of view, when we make a chip, we have to start thinking of the process node, right? Like some nodes are leakier than others. So when we're designing a roadmap to be meant for energy harvesting, we have to choose the right fabric node, and that in turn changes the cost. From then, we really have to think like voltage in. There's no simpler way to think about it is V in. So we design our interior DC-DCs for all the new range of battery chemistries, right? That's something new. We didn't have to think about that before. Now we have to think about that in a way that our end customers can use as few passive components as possible, right? Keeping that cost in mind. And as we work our way up to firmware and software, at the platform level, all the peripherals of an SoC, like, cold starting, waking up, reading flash, going in and out of sleep, that's stuff that we're really sharpening the pencil and shaving off every microjoule, because not only are the likes of the harvesters asking for this, our end customers are now savvy to it, saying, I need to be able to wake up in 16 microjoules. That was unheard of 10 years ago. And then finally, to enable the market in the IoT, which is emerging and very exciting as it is, we've realized we can't do it alone. We need so many partners along the way, and we have to make the solution doable. We have to make reference designs, sample examples. We have to make firmware that is energy aware. So an algorithm that knows its energy and then dynamically changes its payload, or changes the PHY, or extends its sleep. So I'm happy to say we're only at the very beginning. So it's a very exciting spot for semiconductors on my end of the equation, right? I'm at the opposite end of the equation. So good question.
So listening to you, I think it's about it's not only about the fabric or the architecture of the MCU, it's also about how you work with other partners and how you enable the design engineer to how you make it simpler and easier for them to be able to access the technology and create the application. I have a related question though, because once engineers have made that choice on device, the next challenge is firmware development. So with that thought of how do you make it easier for engineers to engage, what tools, development kits or resources does Silicon Labs provide to help engineers get started quickly and ensure they're designing with low power in mind from day one?
Yeah, that's another good question, because that's what makes or breaks the whole story here, right? The market won't succeed if it's too hard to do. And a big fear of ours was that fear of abandonment, where the engineers were like, I know this is possible, but it's very hard to develop, and it takes me 24 months to get my product out. So what we've done is made dev kits that exist on our existing platform, and that you can convert an existing product to go batteryless. So I say simple, it wasn't simple. We had to change all of our sample applications, all of our application notes, because like I said, it wasn't a use case we were catered to before. And then all of a sudden it was like, no, people are doing this. We have to make sure our documents take care of that, our software examples take care of that, and that we're compatible with all the different storages, and we're compatible with all the different harvesters. And it's a challenge because there's more and more and more of them, and like you said, there's more and more applications we haven't thought of. So we've gone down a dev kit approach that allows you to measure things, allows you to know your budget, know your max, know your peaks, know your averages, and equipping our team to answer those questions, right? So it's, again, we're at the very beginning, but we're doing that in mind. We have dev kits. You'll see them at our booth in action, and then the sky is the limit for end customers to build what they want with it.
Thank you. Yeah. So you talked about some of the measurements required there, I think. So Björn, let's move on to Qoitech and Qoitech's technology. And listening to all of this, the key to successful deployment of a batteryless, let's call it IoT node, lies, I think, in balancing the minimum power budget that you can get away with and in your application, or what your application can stand, with a power source capable of reliably delivering it. So what do you see as the key challenges for design engineers in this scenario, and how can Qoitech help them?
Okay, so we have talked a lot about what the developers need to know, and what we help with for the developers is that they can test, they can see it live, that they do have the lowest power budget for the device. I mean, one key part of this is to have, for the device in itself, to have the lowest possible power consumption, because if you have a low power consumption, it makes high freedom for how you select the energy harvesting system, and all of this must be tested for the different key components in the system, like testing the PV cell to see how does the PV cell change how much energy you can get from when you get in different modes, like when it's being scratched, when it is dirty. This can and should be measured, so you really know what will the end device, how will it function, so you don't get unhappy afterwards. You should really know what will happen. And for the different levels, you should verify and see it for yourself that it really works, and test the different to see that you have selected the right components, the right power management IC, that you have everything correct to get the best solution.
So from a practical standpoint then, if you're talking about testing the application to make sure that it's running at the sort of the ultimate low power state that it can run in, what are the kind of things that engineers would consider? And again, how does the Qoitech toolchain help them understand that against, for example, their code, when their code's running?
So we make it possible for the developers to synchronize the firmware development to see more or less how every line of code, how this affects the power consumption. So this makes it possible for the firmware developers to directly see how their code really impact the power. So it's not up to only hardware developers. The hardware developers, of course, have the responsibility to make the most power efficient hardware, but it's also up to the firmware developers to not ruin this excellent possibility that can come. And this is easily tested by, you can then synchronize the bug logs to see the power consumption and see how the actual firmware, how this affects the power consumption.
So it's a combined approach then, really, isn't it? As well as being able to test the hardware in a real world application rather than just taking it from a data sheet. So I guess when we take everybody's inputs in total, we are talking about system level consideration, aren't we? As ever, I think with any application. I just wonder if anybody in the crowd is working on any wireless, energy harvesting powered wireless sensor nodes. Do you have any questions for the panel members? Don't be shy, they don't bite. If anybody would like to ask anything. None of you are working on anything? It seems not. So okay, so we'll draw the panel to a close then at that point. I would like to thank all of our guests for their excellent contributions. It's really interesting to hear that sort of end-to-end story from the early days of EnOcean, from things like needing to develop new wireless protocols to be ultra-low power, as well as new MCU fabrics, having the tools in order to optimize your, or let's say for energy optimization, to make sure that that application is using as little power as possible, and also thinking about what the application scenario is for the power source that you're going to select as well. So many different aspects, and hopefully you've all found that useful for whatever it is you're currently not working on, it seems. Thank you.